Hey everyone, and welcome. Today we're going to dive into some of the hidden chemistry that's happening all around us, every single day. We're going to connect two mysteries that seem totally unrelated, one about your soda and one about the fish in a lake, and show how they're solved by the exact same powerful idea. Let's get right into it.
Okay, first up, a question we've all wondered about. You've been there, right? You leave a can of soda out on a warm day, and just a little while later, all that fizz is gone. But if you pull one straight from the fridge, it seems to hold its bubbles forever. So what's going on there?
And for our second puzzle, let's think about aquatic life. A cold, deep lake can be absolutely packed with fish, just thriving. But a shallow, warm pond in the middle of summer, you might see fish gasping at the surface. And believe it or not, the answer to why your soda goes flat is the exact same answer to why those fish are struggling. Let's figure out what it is.
All right, so to get to the bottom of all this, we first need to grab a tool from the chemistry toolbox. We need a way to measure how things are mixed together. And in the world of science, this is called concentration.
Concentration is really just a fancy word for how much stuff is dissolved in a liquid. Think about making coffee. If you put in 1 spoonful of sugar, you've got a weak or low concentration solution. But if you dump in 10 spoonfuls, whoa, now you have a very strong, high concentration solution. It's simply the language chemists use to be super precise about the mix.
So one of the most common ways chemists measure this is something called molarity. And yeah, that's with a capital M. It's basically asking how many molecules of the solute, our sugar, are packed into a specific volume of the solution, and that volume is typically 1 liter. You can kind of think of it as a measure of molecular density. And here's a really simple way to remember it. For molarity, volume matters. Now this is a crucial detail, because what happens when you heat up a liquid? It expands, right? Its volume changes, and that means your molarity measurement can change too, even if the amount of stuff dissolved in it hasn't changed at all. Now, to get around that whole temperature problem, chemists have molarity's cousin, molality, this time with a lowercase m. To make things stable, molality just ignores volume completely. Instead, it measures the molecules of solute against the mass of the solvent in kilograms. And a kilogram of water is a kilogram of water, whether it's frozen solid or boiling steam. Mass doesn't change with temperature.
So the memory hack here is just as simple. For molality, mass matters. This makes it the perfect tool for scientists who are studying how things react at different temperatures, because their starting measurement is always going to be stable and consistent.
But what if you're trying to measure something that's, well, barely even there? I'm talking about a tiny, tiny amount of a pollutant in a huge lake. For that, scientists use parts per million, or ppm. It's designed for measuring incredibly small or dilute concentrations.
And the way to remember this one is pretty straightforward. Just think ppm for pollution problems. If you've ever looked at a water quality report or an air quality index, you've probably seen this unit. It is the absolute standard for environmental science.
Okay, so let's put all that together. What's really interesting on this slide is that last column. See that? Molarity, because it's based on volume, changes with temperature. But molality and ppm, since they're both based on mass, they don't. They stay constant. This distinction is the first major clue to solving our mystery.
Okay, so now we know how to measure a mix. But there's a limit, right? How much can you actually mix into something before it just stops dissolving? Well, that brings us to our next key concept, solubility. Solubility is the limit. It's the absolute maximum amount of something you can dissolve into a liquid under a very specific set of conditions. Think of it like a breaking point, where the liquid just says, "All right, I'm full, no more."
And this leads us to two basic types of solutions. An unsaturated solution is like that first spoonful of sugar you put in your coffee. It dissolves easily, and there's clearly room for more. But a saturated solution, that's the 10 spoonful, when the sugar just gives up and sinks to the bottom. The coffee just can't hold anymore. It has reached its solubility limit.
Oh, and just a quick side note on what dissolves and what. The golden rule here is like dissolves like. It's pretty simple. Polar things like sugar and salt dissolve really well in polar liquids like water. Nonpolar things like oil, they just don't. It's as simple as that.
All right, we have our tools now. We understand concentration and we understand solubility. Now it's time to apply them. And this is where it gets really interesting, because solids, like sugar, and gases, like the carbon dioxide in our soda, behave in completely different ways when they dissolve.
So for solids, heat is your friend. I mean, if you want to dissolve more sugar, what do? You heat up your tea, right? A higher temperature almost always increases the solubility of a solid. But what about pressure? Turns out it does basically nothing. You can't squeeze more salt into water.
Now let's talk about gases, and here it is, our second huge clue. They're the complete opposite. A higher temperature makes gases less soluble. They actually want to escape the liquid. But pressure does the opposite. The more you pressurize a gas, the more of it you can force to dissolve into a liquid.
And this table right here illustrates that key difference perfectly. It's our aha moment. Look at this. As temperature goes up, solid solubility goes up, but gas solubility plummets. As pressure goes up, it does nothing to solids, but it dramatically increases how much gas you can dissolve. These are opposite behaviors, and this is the answer to our puzzle.
So now, let's see how this plays out all around us, from a simple soda can all the way to the deep ocean. We can finally connect these rules back to our original mystery.
That rule for gases and pressure actually has a name. It's called Henry's Law. And it simply states that if you want to dissolve more gas in a liquid, you've got to crank up the pressure of that gas above the liquid. This is the science behind every fizzy drink you've ever had.
Here's exactly how it works. Inside a sealed soda can, the pressure is incredibly high, and that's what forces all that CO2 gas to dissolve in the liquid. The moment you crack it open, that psst sound, you release all that pressure. Instantly, Henry's Law kicks in. The liquid can't hold that much gas anymore, so the CO2 makes a run for it and escapes as bubbles. And a warm soda? The heat lowers the solubility even more, so the gas rushes out that much faster, leaving it flat.
You know, this isn't just about drinks. Henry's Law governs things that are matters of life and death. For scuba divers, coming up to the surface too fast releases dissolved nitrogen in their blood as bubbles, causing a very painful condition called the bends. At high altitudes, the lower air pressure means less oxygen dissolves into our blood, which leads to altitude sickness. And now, back to our fish. Cold water holds more dissolved oxygen because of these exact same rules, allowing them to breathe easy. A warm, shallow lake has less dissolved oxygen, and that's why they struggle.
So there you have it. From the fizz in your can to the oxygen in your blood, it's all being governed by these fundamental rules of how gases and liquids mix. It really makes you wonder, doesn't it? What other invisible chemistry is shaping your world right now? Thanks for joining us.